A rocket launches vertically from a launch pad, and 5,000 feet away from the launch pad there's a camera recording the rocket as it goes up into the air. We are asked to figure out the rate of change for this camera's angle so that we can keep our camera on the rocket as it's rising. We specifically want to know what the rate of change for the camera is when the rocket is 1,000 feet above the launch pad, because that's where we have the recorded velocity for the rocket of 600 feet per second. We can see that there's multiple things changing in this diagram, so let's break it down into 3 different stages. In the beginning of time, the rocket is just slightly above the ground and the camera has only tilted a slight amount. But as time goes on, the rocket gets taller and taller off the ground, and the angle of the camera gets steeper and steeper, so that angle is growing. We can see that not only is the angle changing, but the height of the rocket is changing. There are other quantities that are changing, but we don't actually need them to answer the question that we're being asked. We do need to know that the angle of the camera is changing as a function of time, and that the height of the rocket is changing as a function of time. Each of these quantities has a rate of change, so the rate of change for the camera's angle would be d theta dt, and the rate of change for the height of the rocket would be dh dt. Now that rate of change is going to be related to how fast the rocket is traveling, its velocity. The given information that we have is that at the moment in time when the rocket is 1,000 feet above the ground, the rate of change, the velocity, of the rocket is 600 feet per second. And it's at that moment in time that we are asked to calculate the rate of change for the angle of the camera, d theta dt. We need to come up with an equation that relates the theta in these diagrams to that opposite side, the height. Notice that we have a right triangle mapping out each one of these moments in time. We can look at this as an angle in the left corner of the triangle, and then the height is the opposite side of the triangle, opposite of that theta. We need to relate theta and h. There's a few different trig functions that I can think of, but there's one that works best here, and that is tangent. The reason being, we know that the camera is 5,000 feet away from the launch pad. So the side of the triangle that's on the bottom, that's the adjacent side to theta. We have that. We know that side. Tangent relates the opposite side to the adjacent side. So tangent's the perfect relationship here. We will use tangent theta, which is going to be equal to the ratio of the opposite side, h, which is changing with time, divided by the adjacent side, which is 5,000 feet, and it stays 5,000 feet no matter what time we are looking at. Now we're ready to differentiate the equation that we have found that relates the two changing quantities. Applying implicit differentiation, we see the related rates equation. We have secant squared theta times d theta dt. That's equal to 1 over 5,000 feet times dh dt. So we have the two rates, and we see that they're related by this equation. We want to solve for d theta dt when dh dt is 600 feet per second. Notice that we don't have to plug in the height of the rocket being 1,000 feet here. But we do have a quantity that we need to talk about. In order to solve for d theta dt, I need to know theta, or rather I need to know secant squared of theta. That's where the height of the rocket is going to come into play. We can imagine that when the rocket is 1,000 feet above the ground, and the camera is, which is always 5,000 feet away from the launch pad, that we can calculate theta in this instant. We could use a trig function to tell us exactly what theta is, or we can recognize that the equation calls for secant squared theta. So if we can come up with a ratio for secant, then we can just plug that into that square. Secant is the ratio of the hypotenuse divided by the adjacent side. We know two sides of our triangle, so we can use them to find the hypotenuse. The hypotenuse would be the sum of the squares of the two legs of this triangle, and then square rooted. We can see that the hypotenuse has to be 1,000 times the square root of 26. Using that, as well as the adjacent side of 5,000 feet, we can come up with a ratio for secant theta. And let's simplify that. We'll divide off a factor of 1,000. So secant of this angle, we don't know what the angle is, but we know that the secant of it is the square root of 26 divided by 5. So that's what we're going to plug in to secant squared. So we will have the square root of 26 divided by 5 squared instead of secant squared theta. Plugging these values in, we have the square root of 26 divided by 5 quantity squared times d theta dt, and that's equal to 600 feet per second divided by 5,000 feet. Now the first thing I want to do is divide off a factor of 100 on the right-hand side. So we can divide off those zeros there, leaving us with 6 over 50. But also we can reduce some units. Feet divided by feet is equal to 1. So on the right-hand side we will have 6 over 50, and that will be per second. So we don't have any feet over there anymore. On the opposite side, secant squared theta turned into the square root of 26 divided by 5 squared, we can evaluate that to be 26 over 25. We're a little bit closer. Remember, we're trying to solve for d theta dt. So I'm going to multiply both sides of my equation by 25 over 26 so that I can cancel out the 26 over 25 that is being multiplied to d theta dt. Now we have d theta dt isolated, and our units are radians per second. The 1 over seconds was already there. We got that from the dh dt rate, but the radian came in from the secant squared theta. We were talking about a unitless ratio from a triangle, and technically we would use radians in this case. So we have radians per second for our units, and now we're just left with simplifying 6 times 25 divided by 50 times 26. We can reduce the 25 and the 50, and then we can reduce the 6 and the 2. That leaves us with 3 over 26 radians per second. So the angle of the camera is rotating at a rate of 3 over 26 radians per second at the moment in time when the rocket is 1,000 feet above the launch pad.